Welcome to 11.3 Reactions of Halide Ions. If you need help in your textbook, then look at pages 170 to 172. So our lesson objectives for today are to understand the trend in reducing ability of the halide ions, know the different products formed by the reaction of NaX and sulfuric acid, understand why acidified silver nitrate solution is used as a reagent to identify and distinguish between fluorine, chlorine, bromine, and iodine, and know the trend in solubility of the silver halides in ammonia. So first things first, halides are reducing agents, so you already know that reduction is the gain of electrons. Therefore, a reducing agent is a species that's going to lose electrons because it's going to give them away to something else and cause that to be reduced. So halide ions are reducing agents. You already know that halide ions are -1 charged. So halide ions are reducing agents, and as you go down group 7, they become stronger reducing agents. And the reason they become stronger reducing agents is they become better at giving that, giving away that electron. And that's because as you go down group 7, the ions become larger. So the outer electron is further away from the positive charge of the nucleus, so that makes the attraction weaker. The attraction is also weaker because you've got increased shielding, because as you go down, each one's got another shell of electrons that's filled. So both of these two factors outweigh the increase in nuclear charge, and this means that as you go down group 7, they become better at giving away that electron. So I- is better than Br- is better than Cl-, which is better than F-. Now you need to know about the halide ions reacting with concentrated sulfuric acid, and this reaction is a demonstration of the difference in reducing power. So we've already said that Cl- is a weaker reducing agent than Br-, which is weaker in turn than I-. So when you've got Cl- as a halide ion, it reacts with a sulfuric acid. Because it's a weaker reducing agent, there's no redox reaction happening, and so all you get is a simple acid-base reaction. For the Br-, that's a stronger reducing agent than the Cl-. So after you get the initial acid-base reaction, then the Br- ions then reduce the sulfuric acid to give sulfur dioxide. And for the I-, that's an even stronger reducing agent, which means after the initial acid-base reaction, the iodide ions reduce the sulfur in sulfuric acid to give sulfur dioxide initially, then to give sulfur, and then finally to give hydrogen sulfide. So these reactions can be summarized in this table that shows the halide ions reacting with concentrated sulfuric acid. So the grayed out bit means that, that's not applicable, so there isn't anything to go into that box. So sodium chloride is a simple acid-base reaction. You end up with NaHSO4 as a solid, and you get HCl as a gas. And you actually see the HCl given off as steamy fumes when you do this reaction. So obviously you have to do it in fume hood because you don't want to cause yourself any harm. So the exam board does actually expect you to know the observations. So it is a common exam question to ask you to describe what you would see when these reactions happen. So you do need to be aware that what you would see when that reaction is the HCl being given off as steamy fumes. So for the sodium bromide, first of all, you just like the sodium chloride, you see steamy fumes. So in this case, it's HBr. So you see the steamy fumes of HBr being given off, but then the Br- then reduces that, the sulfur further, and you end up with sulfur dioxide and water and bromine. So what you see initially is the steamy fumes of HBr, but as the reaction continues, you'd see brown fumes of bromine. You'd also get the colourless gas, sulfur dioxide, being given off. Although because it's colourless, you wouldn't easily see it. So for sodium iodide, it's similar in that you initially get the acid-base reaction gives you NaHSO4 and Hi, and again you see the Hi given off as steamy fumes. You then have an intermediate product, so you'd have some colourless sulfur dioxide being given off to give SO2 and 2 waters and I2, so you'd also see the black solid of iodine at that stage. Yes, the sulfur dioxide then gets reduced further to give sulfur, at which point you see some yellow solid sulfur, and then it gets reduced even further to give hydrogen sulfide. You've got H2S, and that, although you won't see that, if you didn't have this in the fume hood, you would be very aware of that gas being given off, because it's that classic bad egg smell, that classic rotten egg smell. And again, you'd see some more iodine forming, so you'd see that black solid of iodine. So make sure you learn. You should the products that you're given, the observations that you make, and you should be able to write equations to show what products you get. So what you also need to be able to do is use the silver nitrate and ammonia to identify halide ions. This is something that we've met at GCSE, but we do it in a bit more detail at A level. So the procedure is, first of all, you have to add dilute nitric acid, and the reason you do this is to remove any soluble carbonates or hydroxides, because if you've got carbonate or hydroxides dissolved in your solution, then when you add silver nitrate, the silver nitrate will react with the carbonate or the hydroxides to give silver carbonate and silver hydroxide, and both of these are insoluble, so you get a precipitate. So this will give you a false positive. So we have to add the dilute nitric acid to make sure that we are testing just for the halide ion. So once you've added the dilute nitric acid, you add a few drops of silver nitrate solution. You then observe the colour of the precipitate, and then you add dilute ammonia and observe whether the precipitate dissolves. You then add concentrated ammonia and observe whether the precipitate dissolves. And on this slide, it tells you the observations that you would make for each halide. So for fluoride, the silver product would be silver fluoride. There wouldn't be any precipitate because silver fluoride is soluble in water. So obviously that then doesn't have any solubility in ammonia because it's already dissolved in aqueous solution. So for chloride, the silver product that forms is silver chloride, which is a white precipitate, and that dissolves in dilute ammonia solution. The bromide would give you silver bromide, which is a cream precipitate, and that dissolves in concentrated ammonia, but not in dilute ammonia. And the iodide will give you silver iodide, which is a pale yellow colour, and that's insoluble in both concentrated and dilute ammonia solution. So the reason we use the ammonia is because if you look at the colours, they get slightly darker as you go down, so they go from white to cream to pale yellow, but there's not much of a colour difference. So if you see them compared to each other, then you can quite often work out which one it is, but it's a bit of a judgment call. So the ammonia just helps you make that definitive call that yes, it's chloride because it's white and it's dissolved in dilute ammonia, or we're not sure if it's white or cream, but it doesn't dissolve in dilute, it dissolves in concentrated ammonia, therefore that would mean it would be the bromide. Back to our lesson objectives, which were to understand the trend in reducing ability for halide ions, know the different products formed by reaction of NaX and sulfuric acid, understand why acidified silver nitrate solution is used as a reagent to identify and distinguish between fluoride, chloride, bromide and iodide, and know the trend in solubility of the silver halide in ammonia. So as usual, if you don't understand anything to do with those lesson objectives, go back and rewatch the video or use your textbook so that you make sure that you understand it before you come to lesson.